grade 12s. Welcome to another virtual session for the UPA Saturday School. And welcome also to any other grade 12 learners who might be watching this lesson. Grade 12s, we can now start looking at how to plan an investigation. So the knowledge area this lesson comes from is chemical change, because we're looking at the rate and extent of a reaction. So, exactly what experimental design to select with your experiment planning? I first want to go through what you should be able to do from CAPS. Okay, firstly, you need to explain what is meant by reaction rate. You also need to list the factors that affect the rate of the reaction. Those will be your factors to control in the experiment. You also need to be able to suggest a suitable experimental technique for measuring rates of reactions. And more importantly, you must develop knowledge and skills related to scientific inquiry and an understanding of the nature of science. Hence, our focus on planning the investigation. I would like us just to recap what we saw in the introduction. So, firstly, we saw the chemical reaction between vinegar, which is acetic acid, and baking soda, sodium hydrogen bicarbonate, in the video How to Explode the Plastic Bag. Now, Camilla showed you how to prepare the reactants to get the plastic bag to explode. Firstly, you put 4 tablespoons of baking soda into the paper towel. Then he poured vinegar into a plastic cup after he had made the paper towel package with the baking soda. He then put the vinegar in the plastic bag. Now, he put the towel inside the plastic bag, but he didn't mix them yet because he wanted to seal the bag first so no carbon dioxide would be lost. Once the bag was sealed, only then did he drop the baking soda into the plastic bag. Immediately, you saw gas bubbles as the reaction started. So you saw the sealed bag begin to expand as the carbon dioxide gas was produced during the reaction. So Camilla holds the expanding bag over the large cup. He knows it's going to explode soon. He drops the large bag just before the explosion. He's a little bit nervous, but the bag explodes, and you heard him squeal with the explosion. So even though he was prepared for it, it was still unexpected. So the things that I would like you to focus on right now. He knew that this reaction would happen quickly, but he wasn't sure exactly how long, so it still took him a little bit by surprise. So my question is, how did he know he would be able to shoot this video before the bag exploded? So you probably think I have a step-by-step procedure or method to follow to help you to design your experiment. And that's where I really encountered my first problem, because there's no such thing as a set scientific method. Does that mean that scientists don't have a method to investigate problems? No, it just means that there's no one method. There are various methods. It really depends on what you're trying to investigate. Let's by asking an actual scientist, Teeman Cook, what he thinks about the scientific method. He is a scientist and he has been a science teacher.
The scientific method sucks. Now, by that, I don't mean that science sucks. As a physicist, I believe that science has had countless benefits for humanity. But when I was in 8th grade, I learned about this thing called the scientific method. And since then, I have done science, I have worked with other scientists, and I've taught science to college students, to K through 12 teachers, and to 7th and 8th graders, middle schoolers. And from these experiences, I've come to the conclusion that the scientific method sucks. If it's been a while for you, as it has been for me since middle school, let me run through it real quick for you. First of all, step 1, identify a problem. Step 2, do some research. Step 3, form a hypothesis. Step 4, do an experiment with some independent and dependent variables to test your hypothesis. Step 5, analyze data. Step 6, draw a conclusion. It sounds good, right? It certainly matches what we see on TV and in movies and what we see on the news. Unfortunately, it completely misrepresents what scientists do and what science is all about. And this manifests in four main ways. First of all, it's incredibly linear. We start with a problem statement and we end with a conclusion. This implies that science is something that's once and done, fixed for all time. Secondly, it's not very intuitive. How do I choose a problem? What do I do with my conclusion when I'm done? If I have no idea what should or even could happen, how do I come up with a hypothesis? This makes the process intimidating and dangerous. 3, there's a focus on conclusion, reaching the conclusion, on getting a fact. Well, what happens when the information changes? What happens when facts change? How does this process capture that? And finally, the focus on experimentation. Now, don't get me wrong. I'm a big fan of teaching students to control for whatever random variables they can. But there's been a lot of really good science that's been done without being able to control for, well, any.
Tiemann says this linear representation of the scientific method is what sucks. It makes people think science is intimidating and difficult. And therefore, many people don't want to become scientists. And it goes against intuition. What he says, it's rather better to think of this cycle of thinking where you can change your ideas. You see something, it doesn't work. You go back, you change again. So science is this cyclical process, not this linear process that the scientific method makes people think it is. Ji-Woon Park, who is a research chemist, gave a talk where she talked about how she applies the scientific method to solving problems in her work life or in her everyday life. But one of the things she says is that she has found the scientific method to be very versatile. Saying that she found the scientific method to be very versatile is a way of saying it's not the step-by-step process that you are presented with in textbooks, but it's something that you can adapt and modify as you work through your scientific research or do your scientific investigation.
How many of you consider yourself as a scientist? Okay, I see a few hands in the audience. How many of you have ever done a scientific experiment? I'm seeing more hands. That's a good sign. Use the scientific method. If the term doesn't ring a bell, perhaps this chart jogs your memory? Okay, well, in the next few minutes, I hope to convince you that all of us are scientists. And as a chemist, my everyday job involves applying the scientific method to unknown chemical questions. Perhaps emanating from my days in lab, I've come to appreciate the versatility of the scientific method. As you may imagine, experiments almost never work the first time. My original hypotheses, whether it was in lab or my love life, have rarely been accepted on the first try. I'm sure that this will not be the last iteration of our hypothesis, because in science, the more data that you gather, the higher confidence you have in supporting your hypothesis. So now you may be wondering, how can you apply the scientific method to your own lives? Let's take a pretty common example that all of us face, commuting. How many of you take the same commute route to work every day? Okay, I admit I'm also guilty of this. But interestingly, there's a study that shows that the scientific method could be very helpful in optimizing our commute routes. In 2014, workers in the London subway station went on strike. As a result, several tube stations were closed, forcing commuters to experiment with alternative routes. Researchers at Cambridge and Oxford found that those who actually experimented with alternative routes were significantly less likely to return to their old routes after the strike ended, compared to those who had not experimented during the strike. This shows that commuters were able to find a more optimal route after they were being forced to experiment. In light of this, perhaps we can ask a new question about our own commuting routes and test a hypothesis, which could involve using a different mode of transportation or getting off at a different subway stop. I think in this scenario, using the scientific method could be more insightful than using Google Maps. And if you're late to work while testing your hypothesis, I am not responsible for that. All right, so beyond commuting, I encourage you to ask yourselves how you can apply the scientific method in other aspects of your lives. We've all been doing this in some way or form, subconsciously or consciously. But to really get you thinking on this, I wanted to leave you with 3 last suggestions based on my experience as a chemist, not as a life coach. First, it's okay to be unsure. Regardless of how systematic we try to be, every model, including the scientific method, has exceptions and errors embedded. We try to be perfect, but as humans, we make mistakes in the analysis or experimentation, often without a logical explanation. In science, you have the opportunity to try again. You get to try as many times as you want. In some cases, your experiment may be an infinite loop. Finally, acknowledge that failure is not really a failure. The inventor of the light bulb, who you may all know, Thomas Edison, said that if I find 10,000 ways something won't work, I haven't failed. I'm not discouraged because every wrong attempt discarded is another step forward. In science, you can either accept, reject, or fail to reject a hypothesis, but never just fail a hypothesis. The results of one bad experiment become the basis for future questions and hypotheses. All of us are scientists of our own world. The questions we ask are unlimited. The experiences we have are never failures, and the entire world is for us to explore. Thank you.
Ji-Woon Park used this diagram for her model of the scientific method. This model of the scientific method, I want you to see the arrow going from conclusion back to hypothesis. So if your hypothesis or your conclusions mean your hypothesis is rejected, all it means is we try again. You look at adapting your hypothesis, and you try and you experiment again. You try something else. You modify your method. It's all about the process. You try again. So unfortunately, in school science, and because of the limited time you have to conduct a practical, you might think that if your hypothesis is rejected, you're incorrect. No, that is all part of the learning process. And it is exactly how science works. A rejected hypothesis just brings you a step closer to finding the answer, because you know it can't be that method, so let me go with plan B. So before I even ask you to develop your own question or hypothesis, I want you to remember that this is how science works. Scientists are always re-evaluating their hypothesis. New evidence is brought in, they have to rethink their theories. Science is a changing body of knowledge based on the things that we see. So the scientific method per se, I want you rather to think of this cycle of scientific thinking. And it's this cycle of scientific thinking that makes using the scientific method good for problem solving.